In legged robotics, no amount of sophisticated math can save you from basic reality. Ground friction detects everything. If the friction is too low, the foot slips, the leg extends, the motor fires, and the robot states backward, generating zero forward propulsion. The transition from a stance to swing phase becomes a struggle, causing a jerky, lurching gait that drains battery power and destabilizes the body. You can spend months writing a perfectly balanced gate controller, but if the ground contact parameters in your physics engine are improperly tuned, the controller will fail. Configuring foundational contact physics is the absolute prerequisite for any successful robot simulation. To get those parameters right, we have to look closely at the exact moment a robot's foot touches the ground. The engine computes a ground reaction force. The vertical normal force supports the robot. The horizontal friction force resists starting, and maximum friction equals a normal force time mu. This creates a geometric friction cone. A larger friction coefficient geometrically widens this cone. That expanded boundary is exactly why rougher surfaces allow a robot to execute aggressive acceleration and tight turning forces without losing a traction. That stationary geometry explains a flute planted firmly on the ground, but locomotion requires a constant transition from a planted stance to lifting the legs for a swing. Before the foot moves, it is held in a place by static friction. This is a high resistance force that grips the ground while leg is loaded. Resistance climbs to the high peak of the static friction, but the instant the foot slides, forces breaks free, dropping instantly to lower kinetic baseline cross, creating a stick slip behavior. On a physical hardware, this suddenly drop in a resistance is visible. A standard rigid body solver like ODE, Dart, or Bullet do not model this complex two-part curve by default. Instead, the solver compresses the physical interaction into a single breakaway threshold because the solver relies on the single value simplification, the simulated environment, and remains smooth in a ways real hardware is not. This contributes to the gap between simulation prediction and the chatter and slippage observed on the physical robots. To build an accurate model, engineers must translate these continuous physical forces into a discrete parameter of a simulation environment. In Gazebo, this translation happens inside the SDF XML architecture. In the surface block attached to the foot collision geometry, we define friction parameters explicitly, which grip equally in all directions. Now, these two values are usually set identically. So, the zero point 0.7 you type into XML file becomes the single flat line threshold the solver uses to dictate the entire stick slip interaction we just examined. Mapping friction coefficient defines the horizontal boundaries, but the engine also requires an instruction on how the ground itself should respond vertically on the robot's mass. To configure that response, we move to the contact sub block in the SDF file, isolating two specific stiffness or a KP and damping or a KD. So these aren't just arbitrary turning knobs used to stop a robot model from jittering, they represent a specific physical properties. It dictates the exact upward reactive force the ground generates when a robotic foot physically penetrates the floor plane. KD represents the damping force. It exists to dissipate kinetic energy, the exact millisecond of a ground contact preventing the foot from springing back up. But rigid body solver like ODE do not actually run on a simulated spring and dampers. The engine takes user friendly spring values and internally converts them into a constant force, mixing the error reduction parameters to calculate a rigid body states. The variable h in this equation dictates the conversion rate. This h is your simulation time step. Kp and kd form an exact mathematical bridge. Depending on how you tune them, they dictate whether a robotic foot settles perfectly on the floor, bounces wildly into the air, or sinks through the geometrical. When you unite the physical theory of the friction cone with the discrete math of the SDF configuration, you get a fully optimized system. Mechanically, a stable simulation requires keeping all the forces requested by your controller safely inside the Coulomb friction boundary. In software, engineers must consciously anticipate the simulation to real gap. So, the fidelity of the locomotion simulation is tied to these ground contact parameters. Precisely calibrating the interaction between Kp, Kd, and Mu allows a theoretical gate to behave predictively when it meets the digital floor.